Hi everyone, today I'm gonna teach you how to convert from other numbering system to binary system. So we will start with converting from hexadecimal to binary. As we said previously that hexadecimal means 16, so we need 4 bits in binary to represent any digit in any hexadecimal number. For example, if we had 32 in hexadecimal, and we want to convert it to binary, we will need 4 bits for 2 and also 4 bits to represent 3 in hexadecimal. This bit will be our least significant bit, and it holds a value of 2 to the power 0, and we keep increasing the power each time until we reach 2 power 3, which is our most significant bit here. Also, this one will have the same as these bits because we need for each digit in any hexadecimal number 4 bits to be represented in binary number. How can we decide whether to fill the bit with 0 or 1? It depends on some conditions. So you will take 2 as a separate number and compare it with the most significant bit, which is 8, and this one will be 4, 2, 1. 2, is it less than or equal, is it greater than or equal to 8? If the answer was no, you will fill the bit with 0. So let's continue. Is 2 greater than or equal to 4? The answer is no, so also this one will be filled with 0. Then 2, is it this number, is it 2 greater than or equal to 2? Yes. So we will fill this bit with 1, and then we take this value with our value, which is 2. 2 minus 2 will give us 0. Then we'll take this number, compare it with 1. Is it greater than or equal to 1? The answer is no, so we'll fill it with 0. And we're done with the first part. Then we will move to the second part, which is 3. We will do the same steps. This is our least significant bit, and this is the most significant bit. We have here 2 power 0. We keep increasing the power until we reach 2 power 3, which is equivalent to 8. This one 4, 2 and 1. We will compare 3 with 8. Is it greater than or equal 8? The answer is no, so we'll fill it with 0. Then 3, is it greater than or equal to 4? So the answer is no, fill it with 0. Then is it greater than or equal to 2? The answer is yes, so we'll fill this one with 1, and then 3 minus 2, the answer will be 1. And then we compare 1 with 1. Is it greater than or equal to 1? The answer is yes, so this one will be filled with 1. So this is the representation for the number 3 in binary number using 4 bits. We will bring all the bits together. So 3, 2, and hexadecimal is equivalent to 0, 0, 1, 1, 0, 0, 1, 0. And let's clear all this part. So actually, these ones, we don't need them because they don't change anything in the number, so you just can erase them. And here is our number, which is equivalent to 32 in hexadecimal. This is our equivalent number in binary. Now let's move on for the practice question. Convert the following number from hexadecimal to binary. We have this number, and we need to convert it from hexadecimal to binary. We will do the same as we did in the previous example. We'll take C, but first of all, we can't just convert C because you don't know what is the what does it C mean. So you need to convert it to decimal, because Actually, we can't just convert C to binary directly. Like this is the hexadecimal, and here we have the binary system. We need to pass through another station, which is the decimal. So we didn't do the same here because 2 is equivalent to 2, and like here's the hexadecimal. 2 in hexadecimal is equivalent to 2 in decimal system. So we didn't do the step and we directly convert. But actually we can't just say that 32 is equivalent to 32 in decimal. This is wrong. We can't say that because these numbers has different values in different systems, and the systems are not equivalent to each other directly. We need to do some arithmetic process to convert between them. So let's return back. So C is equivalent to 12 in decimal. So we will deal with the value of the C, which is 12 in decimal. We need to represent 12 using 4 bits. As we said, we're dealing with a hexadecimal number, so we need to represent the hexadecimal number using 4 bits. So we'll have here 4 bits. This is our least significant bit. This is our most significant bit, starting from 2 power 0. And we keep increasing the power each time until we reach 2 power 3. This one is equivalent to 1, 2, 4, 8. And then now we will start filling our bits. So 12, like, is it greater than or equal to 8? Yes. So we will fill it with 1. And then 12 minus 8, the answer is 4. 4. Now we have 4. We compare it with 4. So is it greater than or equal to 4? Yes, it is. So this one will be filled with 1. And then 4 minus 4 will give us 0. So is it greater than 2? No, so we'll fill it with 0. And of course this one will be also filled with 0. So now we have the first part is done, like the first part in this number is done, which is 1 1 0 0. We will move to the next part. I'm just gonna erase this, and we start comparing. Is it greater than or equal to 8? Yes. So we'll fill it with 1. Oh, sorry, this one. Yes, now we'll fill it with 1, okay? And then 9 minus 8 will give us 1. Is it greater than or equal to 4? The answer is no. So we'll fill it with 0. Then we'll do the same here. Is it greater than or equal to 2? The answer also is no. So we'll fill it with 0. And then is it greater than or equal to 1? The answer is yes. So this one will be filled with 1. So 9 is equivalent to 1 0 0 0 using 4 bits. Now we will move to F. We will do the same as we did for C. F is equivalent to 15 in decimal. This one is in decimal. And this one will be in hexadecimal. And we will do the same as we did previously. We'll start comparing 15 with the numbers here in the values in the bits. So 15 is greater than 8. So we'll fill it with 1. And then we will subtract. So now 15 minus 8 will give us 7. So 7 is also greater than 4. We will fill it with 1. Then 7 minus 4 will give us 3. 3 is greater than 2. Fill it with 1. Then 3 minus 2 will give us 1. 1 is equal to 1. So we'll fill it with 1. So now we're done with the last part. And the number that is equivalent to the binary number that is equivalent to this number is this number when we bring all these together. This number in hexadecimal is equivalent to 1111 101 1001 1100 in binary. Now we will move to the next one, which is converting from octal to binary. We will do actually the same, like it's something similar to what we did in hexadecimal. As we said previously, that octal means 8 and we need 3 bits to represent any digit, like we need 3 bits using a binary system to represent any digit in any octal number, okay? So let's take an example. If we had, for example, 16 in octal, so this one we need actually now to convert it to binary. This one will need 3 bits and this one will need 3 bits also. This is our least significant bit and this is most. The value of this bit is 2 power 0, 2 power 1, 2 power 2. Also we have the same here. And now we're going to do the same to decide whether to fill the bit with 1 or 0. 4, 2, 1. So is it greater than or equal to 4? The answer is yes. So then we'll say that 6 minus 4 will give us 2. 2 is greater than or equal to 2? The answer is yes. So we'll fill it with 1. Then we take this value, 2 minus 2. It will give us 0. Then 0 is not greater than or equal to 1. So this one will be filled with 0. Now let's do the same for the second part. Oh, I'm sorry. This one was 110. Here, 1. Is it greater than or equal to 4? The answer is no, so we'll fill it with 0. Then is it greater than or equal to 2? The answer is no, so we'll fill it with 0. Then is it greater than or equal to 1? The answer is yes, so this one will be filled with 1. And then when we write the number in binary, we will say that the equivalent number is 1110. As you can see, we ignored these two because they won't affect the number, and we want to write it in a simple way. Now we'll have an example and we will do the same as we did previously. We'll take 6 and we want to represent 6 using 3 bits because this number is an octal and we want to convert it to binary number. Least significant bit, most significant bit. Most significant bit means the bit that has the greatest value here from, like, among these 3. So this one is the most significant bit, as we have 2 power 2, which is 4. Let's start from 2 power 0, then increase it 2 power 1. Here we'll have 1. And then let's compare. Is it greater than 4? Yes. Then 6 minus 4 will give us 2. Is it greater than or equal to 2? Yes. So then 2 minus 2, 0. This one is not greater than 1, so we will fill this bit with 0. Then let's move to the next one. Just let me write the number here, 110, and move to the next one, which is 4. Is it greater than or equal to 4? Yes, so we'll fill it with 1. Then 4 minus 4 will give us 0. Then 0 is not greater than 2. We'll fill these 2 with zeros. So 1, 0, 0. Then we have 3. Is it greater than or equal to 4? The answer is no. We'll fill it with 0. Then is it greater than or equal to 2? Yes, fill it with 1. 3 minus 2 will give us 1, and 1 is equal to 1, so we'll fill this bit with 1. So now we found the equivalent number for this octal number, which is 1, 1. Here you can ignore the 0 because it won't make any difference. So 3, 4, 6 in octal is equivalent to 1, 1, 1, 0, 0, 1, 1, 0 in binary. And now let's move to the last thing, which is converting any decimal number to binary. Here we have two ways to convert from decimal to binary. I'm going to teach you first the simplest way. It's not actually like most of the books or most of the teachers, they use like what we call the scientific way. It's a bit different, and it may take longer time, but you should really learn it because you may need it, or they may specify the way that you should use. But the second way, you just you can double check or even solve multiple choice question with it, so because it saves really time. So now we have converting from decimal to binary. So let's take this example. For example, if you want to convert 12 from decimal to binary, here we have 2 power 0 power 2. This one will be 16, 8, 4, 2, and 1. We will do the same. We will keep as this one is greater than 12, so we'll ignore it. So we only need these bits to represent this number, 12. Sometimes it may specify in the question like how many bits to use. Actually, they may ask to use like more bits, so it's okay. Like for example, we only need here 4 bits to represent 12, but they may ask you to use 5 bits. It's totally fine. Or they may ask you to use 6. Just do as they say, and just keep following the same procedure as we did, comparing this number with the value of the bits and decide whether to fill it with 1 or 0. So for this one, you want to fill it with, for example, for this one, you wanna use only 4 bits, like the question didn't specify. So you will compare 12 with 8. So 12 is greater than 8, so fill this bit with 1. Then 12 minus 8 will give us 4, and then 4 is equal to 4. We will fill this one with 1, and then 4 minus 4 will give us 0. Then the rest of the bits, of course, there will be zeros, like because this one won't be greater than or equal any value of these, so just save time and fill the rest with zeros. So now we have the equivalent number in binary with 12. This one, 12, is equivalent to 1100 in binary. Now let's move for the practice question, and we have this number 790. You don't know actually how many bits you need, but when you reach a bit with a value greater than this one, just stop and delete that bit, okay? So here we have 2 power 0. And I will calculate I'll find the answer for like the value for each bit, so I can decide whether to stop or continue. 1, 2, 4, 8, 16, 32, 64. This one I think 125. Let me check. Oh, 128. 128. Then this one 256. And then the last one is 512. So let's check 10 power 10. This one will give us 1000. So we don't need it. 1000 or something. So we don't need this one. We'll stop. And then we'll stop here. And this is our most significant bit. Okay. So now 790 is greater than 512. So you fill it with 1. Then 790 minus 512 will give us 278. So then 278 is greater than 256. We'll fill it with 1. And then 278 minus 256 will give us 22. So it's less than 128 and 64 and 32, but it's greater than 16. 22 minus 16 will give us 6. And then 8 is greater than 6, so fill it with 0. But 6 is greater than 4, we'll fill it with 1. Then 6 minus 4 will give us 2. And then this one will be 1. And 2 minus 2 will give us 0. We'll fill this one with 0. So now we have this number, which is equivalent to 790 in decimal. One 0 0 0 0 1 0 1 1 0. So now this way that I'm going to teach you right now, you can use it to convert from decimal system to any other system, because all you need to do is divide the number with the base of this system. So for example, now we want to convert from decimal to binary, so we'll divide by 2, as binary is base 2 system. If you want to convert from decimal to octal, you will divide by 8. If you want to convert from decimal to hexadecimal, you will divide by 16, and so on. So here we have two parts. We have our remainder, and we have the whole number that we are dividing with. So 790 divided by 2 will give us 395. And if we didn't get any decimal point, we will assume that this value is 0, and we will write it here. So here we have 0, and then we convert 395 with 2. We will divide this one by 2. So this one will give us 197.5. We'll take this number and write it here, 197, and divide it by 2. But before moving on and dividing and finding the answer, we have here a decimal number. We'll multiply it with 2, as 2 is our base in this system. So 2 times half will give us 1. So here the remainder is 1. Then 197 divided by 2 will give us 98.5. So multiplying this part with 2 will give us 1, and we take 98 and divide it by 2. Then 98 divided by 2 will give us 49. as we got a number without any fraction or any number after this decimal point, we'll assume that our remainder is 0. Then 49 divided by 2, we will get 24.5. We'll write this number here, 24 divided by 2, but because we have here 0.5 multiplied by 2, the remainder will be 1. Then 24 divided by 2 will give us 12. As we don't have anything after the decimal point, we'll assume that our remainder is 0. So 12 divided by 2 is 12 divided by 2 will give us 6. So we'll assume that there's no number here, that we have 0. And then 6 divided by 2, same, we'll get 3. So we'll assume that there's no number after the decimal point, so we have here 0. 3 divided by 2 will give us 1.5. 1.5, we will take this part multiplied by 2, so we'll get 1. And then we'll take 1, and then because 1 is less than 2, so just write it here. So this is the number, and then when you write the number, you take it from down to up. So the number will be 1 1 0 0 0 0 0 0, then 1 0 1 0, then 1 1 0 1 1 0. So let's check now if it's the same as the number that we got previously. 1 1 0 0. Yes, it is. So you can choose whether you like which way you prefer to solve with, and both of them will give you the same answer. And that's the end of our video, and thanks for watching.